So now I want to say one thing about parallel planning before we move on to real planning graphs. For those in the audience who are grad students or pretending to be, you have to do, I think, parallel planning. And parallel planning is tough. It's hard. It's really hard because the state space is so Mongo. So for example, let's say that there are three actions you can do, A, B, and C. In fact, well, let's just say there are n actions you can do. What's the branching factor for serial planning? Like at most n, right? Okay, what's the branching factor for parallel planning? Even with unit action durations. So you do some stuff, you do some stuff, you do some stuff, you do some stuff. What's the branching factor there? There's some. No, that's a different class. Sorry. It is a bad thing. Factorials are bad, so it's not that. It is another bad thing. What's the other bad thing? Squared is like not good, but I wouldn't say it's bad. Yeah, 2. 2 to the n, because at every time you can either do each of the n things or not. So you have all possible combinations. So it's 2 to the n minus 1. For every action, you can do it or not do it. Except you can't choose to do nothing, because that's just boring. So that's why we subtract 1.
But that 1 makes a huge difference.
Not. Yeah. So it's exponential. So this is why parallel planning is really nasty. So you might be tempted to throw in your hands and say, wow, that's a really big branching factor. 2 sucks to be me. But we can use our brains against this problem. So instead of saying, okay, here's the branch where I do A, here's the branch where I do B, here's the branch where I do C, here's the branch where I do AB, here's the branch where I do BC, here's the branch where I do AC. Instead of that, oh, I forgot to do A, B, and C. Oh, I can't even draw something with that big of a branching factor. Instead of that, we're going to do something called operator decomposition, which actually turns out to help in practice. So first we consider, are we going to do A or not? And if we decide to do A, then we can say, okay, we're done. Or we can say, this is also called the advanced time action. It's kind of a little dummy action. Or we can say, okay, we did A. Now let's consider doing B or not. Okay, now that we've done B, we can consider advancing time. Or we could consider doing C or not. So this is kind of like the not A branch. This is kind of like the not B branch. And we actually don't have a not C branch. I apologize. That's this branch here, basically. So here we have A, here we have AB, and here we have ABC. And then here, in this not B branch here, this would actually be C. So let's see, this represents doing A, this represents doing AB, this represents doing ABC, this represents doing AC. This branch, this not A branch, will actually be labeled B. Well, no, sorry, it won't be. There's a separate level here where we've got B, and then we have not B, which is C. Advanced time. Yeah. So here, this is B, and this is C. So do we have all the? I think we have all the options here. E? Oh, BC. Oh, whoops. Yeah, sorry. This is supposed to be advanced time here, and then this is C. So that's B, and that's BC. Does everyone understand the idea? So I've exploded the tree a little bit.
For ABC, would there be an advanced time between then? Or
there's like an implicit advanced time here. I hate those little skinny things where there's only one child. It just drives me nuts because it's not a real branch point, but it takes up room on your open list. So That's implicitly collapsed there. So if you're doing parallel planning, I recommend this. Now, why is this so much better? I mean, okay, we've got at most ternary branching, but I've increased the depth of the solution by potentially a factor of 3. So why is this better? Why in practice does that turn out to be a good thing to do? Anybody have a hypothesis?
You're making the simpler choices.
Dan.
It looks like you're cutting out half of it no matter what you do.
Each of these things is now a node in our open list, meaning we evaluate its f value. So in a lot of domains, there are a lot of actions that are like obviously bad. Like I'm at the supermarket and I'm trying to buy milk and bananas and I pick up like toilet paper or something. It's like that wasn't one of the things you had needed to do. So rather than expanding all possible actions, like buying each item in the grocery store individually, buying them all in all pairs of 2, buying them in all pairs of 3, all the way up to whatever the maximum number of things you can buy at once is, instead we have a separate action that says like buying the toilet paper, buying the bananas. And the buying the toilet paper one is going to score really bad on the heuristic, even before you pick up the second item.
That's just getting trimmed.
So you're implicitly pruning off all the combinations that involve the toilet paper with one move. All right, is that making some sense? So if you don't like that example, maybe you don't do enough shopping, we could think about a robot. So going along a narrow road in the Italian Alps. They have these little cars in Europe, so they have these little roads. And when they go up mountains like this, they go back and forth, and you're on this little road with this little car, and then a big truck, it comes and turns and it's coming down at you, and you're right over next to the guardrail, and you look down and you see this beautiful vista with olive groves and everything, and you're like, holy shit, I'm going to die. At least I'll fall into a church when I, because there are like little chapels everywhere. All the actions that involve going off the cliff, no matter, regardless of choice of expletive on the way down, you can immediately prune because you just know any combination of actions that involves jumping off the cliff are bad. So immediately you can prune lots of combinations away right away. So this tree, by exploding the operator, it lets you run the heuristic on, like, get a preview with the heuristic of, well, how are things when I use B? Is B just a obviously bad action? And it lets you figure that out. So that's why this is a great way of representing your search space if you're doing parallel planning.
How exactly would you evaluate something like getting the toilet paper? I mean, I know that this isn't an actual case, but what if, say, you need to get the toilet paper as a prerequisite to get milk?
Yeah, you hope your heuristic recognizes that. So we just were talking about the reachability graph. I guess I didn't go so far as to repeat last time's lecture where we talked about H1 plus or H1 sum, maybe we called it, where you add up the levels in the planning graph where the goal literals appear. And if we needed something that required the getting of the toilet paper, then it would appear in a later level because in one of the early levels, the buying of the toilet paper would appear, and that would make something true that was then required by the Holy Grail action. So it would appear in a later level, so it would take that into account. So when you instantiate the buying of the toilet paper, your H value would go down, your G value would go up, your F value would be constant, and in all the other actions, your H value would stay the same because you still hadn't bought the darn toilet paper yet. Your H would stay the same, your G would go up, and your F would go up. So the buying of the toilet paper would look more attractive. Hooray, heuristic search. Oh, that assignment 1 is coming in handy, or at least the thinking is. More questions about this? Yes?
Just to check my understanding.
Okay.
You never ever wanted to do C.
Yeah.
Like you never ever wanted to go down the cliff, ever, no matter what.
Yeah.
That would help you prune this because all the branches that have C, you would just ignore.
Yeah, I mean, it's too bad I ordered them the way I did, because we do have to test C lots of times because we've put it last in the ordering.
But that's what you're saying. That's what you're getting at. That I know that I always want to get milk, and if not getting milk,
if A is the bad action, then life is good. Then this representation is awesome. If A is the bad one, then here you've got A, and here you've got not A, and then this node looks awful, and you don't have to instantiate any of this crap.
Maybe I'm misunderstanding, and this isn't even a question that makes sense in the context, but when we have the negative goals, like we want not B, then what would a heuristic...
Oh, here I'm just talking, this is not trying to represent the state, this is just representing the choice of action to be done. Okay. So at the top of the diagram, these arcs I'm attempting to label them with the combination of actions that were selected. So we're doing action A, action B, action C. Here, I'm exploding this or reconfiguring this tree, and each of these nodes corresponds to doing action A and action B, doing action A and action B and action C, doing action A and action C, doing action B and action C, or just doing action C.
Are we going to have to draw these well, or just understand the concept?
You don't have to draw them any better than I did, which is a pretty low bar.
Because it's not consistent.
The
right side of the tree is not consistent with how you do the left side of the tree.
Because I have this not A thing that's not labeled by an action?
Yes.
So the only time you can substitute an action in there is
If there's one action left to do.
well, except then you wouldn't be able to do one here. Yeah, I should have just made it binary. I should have just had A, not A, B, not B. I probably should have just done that. Whichever way you want, whether you do it binary or ternary, I don't care. Yeah, you probably should be consistent, though. I apologize for that.
But we're not going to have to draw these on